About all projectile problems that are consistently true is that for the most part, the acceleration is usually in one dimension, but the object's traveling in two. So I want to look at the most generic of all examples and talk about what we do about dealing with the information presented. Now, I'm saying this knowing we're going to mix this up and deal with harder examples than this. I just want to get at least a baseline out there of where we start. And where we start is this. You have an object being launched at some initial velocity. I usually always refer to this as V naught. And the purpose for this is we're going to have a lot of different V's in the course of one of these questions. So V naught represents the initial launch velocity. We're talking about the vector velocity. It's usually accompanied with a launch angle as well. Now I'm bringing that part up because your object could be launched some height above the ground. It could be launched some height below the ground. Generally, we don't really know where it's going to land, but we should expect that there'll be some path that will take the object from where it is to the ground. This path is parabolic. That part's not a surprise, or shouldn't be a surprise for you guys. We will prove it's parabolic this year. We refer to the distance along the ground to where it lands as the range. And that's also sometimes referred to as delta x, the horizontal displacement being referenced by the x. And sometimes the height, delta y. Your book uses delta y and delta x for this. Once the object is in the air, no matter where we look at it, it's being acted on generally by only one acceleration. That doesn't have to be true, but we will do no more than one-dimensional accelerations in here. So you won't have to worry about drag actually acting on the object if it's moving in 2 dimensions, because we know that drag acts at an angle. So we're not going to deal with that problem this year. We might deal with the problem of having like a tailwind, which is causing one acceleration in the x direction and a different acceleration for gravity in the y direction. That problem is within our purview, but we're going to focus on the material from kind of last year where this is it, a single acceleration acting in one dimension while the object's traveling in 2. Now, for those of you who do remember this from last year, once the object is launched, no matter where we look at it, the object's horizontal velocity will remain unchanged. Because unless there is a horizontal acceleration, the horizontal velocity has no component of acceleration to change it. So we expect to have a horizontal component that remains the same. I'm bringing this up for a couple of reasons. Since the horizontal component doesn't change, the motion equations that govern it are really simple because they have no acceleration in them. On the other hand, the vertical is acted on by gravity. So we will consider there to be an initial y velocity, which I will reference as v sub y sub naught. That's the initial y velocity. But there will be a y velocity that is changing for all other points in time. This is the one that's acted on by gravity. We can assume that there is some Vy some point in the future, but that value is highly dependent on how long the object has been in the air. The thing that I try to impress upon students is that the horizontal and vertical motion of the object are independent but linked together. So we will study the difference between the horizontal and vertical. Again, they're independent but linked together. I like to provide a framework, something that you can use as a way of organizing yourself. The horizontal information has 3 components: the range, the horizontal velocity, and the time that the object's in the air. these represent the three components that govern the horizontal motion. In the vertical, we're going to have delta y, vy initial, vy acceleration and time. Our standard motion problem with 5 motion variables, assuming uniform accelerated motion. The thing that I always try to encourage you to remember is that the horizontal range is governed by how long the object's in the air, meaning these two pieces of information represent the same value. The time it takes your projectile to move horizontally is equal to the time it takes for the projectile to move up and down. Now, I always think it's a good idea, since these problems deal with vectors, to give yourself reference for positive and negative so that you can be consistent, especially for these variables. If the object lands above where it started, you need to make sure you take that into account for delta y. If it lands below, you need to take that into account as well. The acceleration is likely to always be negative if you choose upwards to be positive. But you can easily throw an object with a downward angle as you can an upward angle. So these, it's critically important you pay attention to whether these have to be positive or negative. Generally, for these problems, you're setting the times equal, but not necessarily always. Remember, some of the things that I'm going to ask of you might require that you bend the rules a bit, like the maximum height. The maximum height doesn't occur when these times are equal. The constraining property is when Vy is 0. That becomes the constraining property. Under these ideas, you'll have to be focused on what's being asked of you to do. Now, it should be clear to you, type 1. I'm going to kind of use the same configuration we had before. And let's make this the marble rolling off the table problem. It's pretty pathetic, but at least it's something that most of you can and have seen. So if the marble rolls off the table, let's say the table is, for argument's sake, the tables that you're sitting at, so it's about 1.1 meter off the ground. And the marble's rolled at 5 meters per second. And as a classic problem goes, where does it land on the ground? All the hallmarks of a basic projectile problem. Just so you guys know, I call this a type 1 problem when I'm working with Physics 1 students. And what makes it type 1 is that there's no launch angle. Okay, no launch angle to start. You just roll something off a table. That means it starts with a horizontal velocity and no vertical velocity. Anytime you can work a 0 into your problem, the problem tends to work out easier. So I'm going to start with that framework because I think that framework works great. Gives us a great place to start. Doesn't solve every problem, but it does a good job of getting us organized. I have range, Vx and T. I have delta y, Vy naught, Vy, A, and T. My framework. My goal here is most likely to find time, either with the vertical information or the horizontal information. So I'm going to start by trying to put in the things I know, but I always think it best to make sure I stop and consider direction. First, the marble has a horizontal only velocity, which means its initial y velocity will be 0 when it leaves the table, and its vertical velocity is going to be the 5 meters per second. The marble is going to fall downwards 1.1 meters. That suggests negative 1.1 meters for delta y. It will be accelerated by gravity the entire time, meaning an acceleration of 10 meters per second squared. And that's it. We're looking for the range. To get the range, it should be pretty clear to you that range is equal to Vx times t. Since there's no acceleration, how far it travels horizontally is how fast it's going sideways times how long it's in the air. And although I know that it's moving at 5 meters per second, I need to figure out how long it takes for the marble to reach the ground. That's controlled by gravity, which is why we need to figure out the time here. Now, this is a problem you've solved before, so I'll wait a patient 30 seconds for one of you to figure out the time. First one down, not too hard, right? You guys who don't remember this stuff, okay. You guys who were never taught this stuff, there you go. That's your first problem. Move on to the second, or do I have to wait around? Do you have any questions? I think that's pretty straightforward. All right, so let's take a look at the next example. Again, I try to break these up in the beginning to try and give us some places to start. So the next one, I'm going to work in a 0 again. We're going to take our same guy, but we're going to launch him at an angle of 5 meters per second from the ground. Now, it makes no sense for it to be horizontal. That's not a projectile problem. So let's launch him at some angle. I'm going to call this a type 2 problem. And again, these first two are just kind of introductory models. I think it would be clear to many of you that the object's going to come up and come back down, striking the ground. That's not particularly parabolic, but it would be a parabolic path. When I consider breaking this up into horizontal and vertical, again, the range Vx t, delta y, Vy naught, Vy a and t. A problem like this really is characterized by the fact that delta y is 0. Although it has a horizontal range, it is going to land at the same height to which it left the ground. That means delta y is 0. Not surprised by that, I hope. But this does add a new wrinkle, something that we didn't have before. Vx and Vy are linked now to what I called V naught, the launch velocity. Now, for just a moment, this means that from now on, you could always write in, just as a reminder, V naught cosine theta here and V naught sine theta here. There's no reason not to. Just make that part of what you think about when you think about projectiles. It was true in the prior example. If the angle was 0 degrees, cosine was 1 and sine was 0. So it was there, it was just not thought about because the angle was 0 degrees. Either way, in these problems, be careful not to just assume that this is positive. They could just as easily give you something that has a negative launch angle. Now, launching something from the ground with a negative launch angle is a little ridiculous because it just gets burrowed into the ground like a bad golfer. But if you're, say, an airplane and you're diving and you drop something like rescue materials for people trapped on an island, it's not uncommon to do that. They would have a declining launch velocity or a declining launch angle. The word declination is the word you have to listen for in a problem if they want to have a negative launch angle. They'll use the word declination or a declining launch angle. All right. All of you looking at me like that's no big deal, so there you go. I think you guys have enough information to tell me where the object lands. I'll wait 2 minutes this time. 2 minutes. Yes, the answer works out to be about 2.5 meters. There's a few mistakes I'm seeing out there, and one of them is actually critically important. So I want to call attention to this. There are 2 times that satisfy this equation, not 1. And I know a lot of you are making this mistake because you think that you can do math this way, and you can't. It's going to be a problem. Let me look at this. Delta y equals 1/2 a t squared plus v naught times t, or vy naught times t. That's what a lot of you are starting with, which is great. 0 equals 1/2 times -10 t squared plus 3.21 times t. There are 2 times that satisfy this equation, not 1. Please stop dividing out by 0, which is what you do when you cancel a t here. We are in a more advanced class now. It's important to understand that we asked the math to tell us when the ball was on the ground. And it was on the ground twice. It was on the ground when t equaled 0 and when t equaled 3.21 divided by 5. Those are the 2 times when the ball was on the ground. I want you to stop throwing away the second time and stop dividing by 0. Does everybody understand? If not, then I'm going to tell you what you need to do. You need to factor out a t and then use your rules for quadratics to set both factors equal to 0. Mathematically, this is the proper way to do it, but in the future, like the very next question, knowing that there might be 2 t's that answer the question, it's important for you to know what the difference is between them, which is why I need you to not throw it away. Now, clearly, one of these t's is more meaningful than the other. I want to know where it is when it lands, which is why I'll use that t to figure out what the range is. That came out to be what, like 0.6 or something? Either way, the range was 3.21 over 5 times 3.83, which gave you a range of 2.45 meters, or 2.5 meters if I have appropriate significant figures. Yep. So the table is 1.1 meters high. The ball is being launched off the edge of the table at a velocity of 5 meters per second and an angle of 40 degrees. I would like where the marble strikes the ground. I am really expecting it to land further away than either of the last 2 problems we've done. That's what I'm expecting. The actual process for doing this is exactly the same as before. We're still going to have a horizontal side and a vertical side. We're still going to try and identify the information that's been presented. Since we've used some of this information before, it's not as hard for us to kind of put this together. First, the object is going to land 1.1 meters below where it starts. It's going to be launched upwards with a velocity of 5 sine 40, which is 3.21 meters per second. It'll be accelerated by gravity at 10 meters per second squared. while traveling horizontally at a speed of 5 cosine 40 degrees, which we also know is 3.82 meters per second. If I choose upwards to be positive and to the right to be positive, then delta y is negative, the acceleration of gravity is negative, my initial y velocity will be positive, and my initial x velocity will be positive. Now, this problem is technically identical to what you've just done. The problem here is finding a time is going to be a little more difficult. You are very likely going to have to use the quadratic formula. You will very seldom get something that's going to easily factor, because we're usually dealing with the sine and cosine of an angle. So become accustomed to finding the roots. And I want to make sure you understand, find both roots. So I'm going to stop now. All right, folks, have a good... And this is me being nice. And I know that you don't see it very often, but here it is. Let's just take into account what I would expect you guys to be able to do on the fly. First, if it's launched at an angle, that suggests it's going to have two components of its velocity. This is why we spent a little bit of time talking about vectors. I need to break up the velocity into a horizontal component and a vertical component, because the vertical component is going to serve as my initial y velocity, and it's acted on by gravity. The horizontal component is going to remain constant. My launch velocity is the hypotenuse of this triangle. So when the object's launched, we need to take this and break it up into its components. Thus, the launch angle that's given helps us dictate that. Again, I don't want to wait around for you guys to remember your geometry, but this one's V naught cos theta. This one's V naught sine theta. Any questions about this?